Welcome back to ECE 442-542. Homework number 3 has been posted. Hopefully you can see that. We are still working through material to get you through that assignment, but hopefully after today you'll have a better feel for how the region of convergence actually connects with those questions. And as a reminder, our next exam is a month from today. Today is 2/14. Oh wow, you have to really perform well because that's Pi Day. That's 3.14. You have to really do well on Pi Day in this next exam, exam number 2. I actually had a student that said he was married on Pi Day at 1:59 p.m. And so if you know the decimal value of pi or approximation, you know it's 3.14159. So I just fell over when he started commenting about his marriage. And then I actually realized that I was married on 2 Pi Day, so go figure. It maybe not at that particular time, but anyway, you multiply 3.14 times 2, now you know my wedding date. June 28th, somewhere. All right, quiz. That's where we will start. And that quiz will work with region of convergence and also a little bit more information. And then we will look at a couple of different examples that remind us why we are concerned about the region of convergence. Why do we need that? And hopefully that will become clear from those 2 examples. Then we will look at the region of convergence, possible patterns for the region of convergence when we simply just have 2 poles. What kind of variety can we expect to have? And so you can imagine what might happen when you have more, but actually we can illustrate the different patterns with just 2 poles. And if you have more poles, we can still have those same kinds of patterns. Then we will get into performing the inverse Z transform and then the impact of different regions of convergence for those particular transforms. Here's question 1 on the quiz. We'll have 4 questions, and to answer, actually I need a visual signal, and the visual signal will be either a thumbs up, a thumbs down, or a thumbs level. And don't signal until I give you the go. So I'll say 1, 2, 3, show me your vote. So with this particular picture, we have the region of convergence shaded, and the question is, for what values of little n is this time sequence x of little n non-zero? When is it going to have some activity? For what values of n? Are those values of n non-negative? That's a thumbs up. Are those values negative? That's a thumbs down. Or is it both values of n, positive and negative? Then that's a thumb like this. And I don't care if it's to the left or to the right, as long as your thumb is level. Okay? Because it's really two-sided. So maybe you could, but I just want you to use one hand. And I want you to hold that hand close so that you can't see what everybody else is doing when I give you the go. Are we ready to vote? Or show me the sign? So now, for what values of n is x of n non-zero? 3 different options. 1, 2, 3. I need you to vote. I wish I had a way of counting. You guys probably sold your clickers, didn't you? And those of you that are online may not have clickers out, but boy, I'd sure record that data if you were listening. All right, so I see mostly people giving me a thumbs up. Is that the right answer? And if it is, why? Do you remember how you could quickly sort of assess this? You could look from the definition of capital X of z and look at the series expansion and examine let's say, a limiting value of z and see if that needs to force particular sequence values, those coefficients, to 0. And in this particular case, I think you will see that since we can actually go to infinity with this region of convergence, it's going all the way out to infinity, we could plug in infinity into this series expansion, and hopefully it's clear that in order for capital X of z to be bounded, we can't have terms over here in the negative time index. And that's then one way to quickly sort of determine which of these three options does this region of convergence correspond to. And in fact, it corresponds to causal signals. So that circled answer is the correct answer. And if you didn't have your thumb up, hopefully by exam number 2, you have a month to learn how to point your thumb according to the question being asked. Question 2 in this quiz. Question 2 is x of n equal a to the n bounded? And here I'm going to give you two options. Is it bounded? We all know what it means to be bounded, right? It's not going unbounded. Unbounded means it's going very large. Bounded means it's well behaved, and a to the n, a is some number that we're raising to different powers. And hopefully you remember what that corresponds to from quiz question 1, what values of n that corresponds to. Okay, ready? 1, 2, 3. I have some thumbs that are dancing. Why do I have thumbs that are dancing? Well, maybe because it's a trick question. Is it not? I haven't told you where A is. Relative to what? The unit circle. I haven't labeled this diagram. And so if 1 was right here, then what could you tell me? Then it's unbounded, isn't it? If 1 actually happened to be out here, then what could you tell me? Then it's bounded. So it really depends. Either of these thumb directions could be justified for answering this particular question. Actually, I wanted you to just try to understand if, for example, what's the magnitude of A need to be in order for a thumbs up decision? Because based on this region of convergence, we know x of n is actually a to the n u of n. I'm using u of n as a switch. U of n will turn that on when the argument inside that step function is non-negative. When n hits 0, that unit step turns on. If n was negative, x of n would be 0. Does everybody see that? The unit step is being used as a switch. Or you could say that this is a to the n for n greater than or equal to 0. That greater than or equal to 0, or that unit step, is what we learned from that region of convergence. What we don't know is the magnitude. If you answered thumbs up, what were you assuming the magnitude on A was doing, or what it was, where was it? You were assuming that that was less than 1. So that gray circle wasn't the unit circle. It was the boundary of the region of convergence. And so I may have misled you by even drawing that gray circle, but that wasn't supposed to be the unit circle. That gray is the boundary, the inner boundary of the region of convergence. And I hope then that you see that if you voted thumbs down or said this signal x of n is going unbounded as n increases, then the magnitude of A would need to be bigger than 1. So there, just pick some A values, a convenient value of A. A equal to 2, 2, 4, 8, 16. You can see that that's growing exponentially. Or for the thumbs down, A equal to a half, 1/4, 1/8. That's shrinking exponentially or decaying exponentially. Are we clear on that being either this or that, depending on what A is, where it's located on the real line? So either of those answers would have been correct, or I could have said, if I was mean, either of those is wrong, right? So, question number 3. For what values of n, and hopefully there's some learning going on here after quiz 1 question and quiz 2's question. Quiz 3's question is, for what values of n is x of n non-zero? Based on this picture for the region of convergence, and again, that gray circle is just the boundary of the region of convergence. So really, it should be kissing A, right? It should be right inside A. The poles can't be in the region of convergence, but it's just on the border. So now, 1, 2, 3. I hope that's not an indication of how you're enjoying this lecture, but thumbs are mostly down, and that's the correct answer for this particular question. And that, I hope, if you didn't have questions 1 and 2 answered correctly, you felt better about question 3. Question 4. If A is bigger than 1 and it's in the positive right half plane of the z-plane, is x of n equaling beta a to the n bounded or unbounded? So now we have to answer. So I guess this question's not written very well, but I guess it should be yes or no, huh? But it's bounded or unbounded by either thumbs up being bounded or unbounded being thumbs down. 1, 2, 3. You guys aren't helping me? It's bounded. Why is that the case? Pardon? N is less than 0, isn't it? So now, based on this region of convergence, we know that x of n is a to the n, where n is less than 0. That we had from quiz 3, or question 3. And now we said that A was bigger than 1. And so now you might say, well, let's just plug in a convenient value. But maybe that's kind of weird to think about. So what you could do is you could say, you know what, let's let L or N equal minus L. If you like to think of positive powers instead of negative powers, then you could say, oh, this is now 2 to the minus L, and what's the value of L? Or what range does it exist over if N is negative? Is that true? So that now we could think of this as 1 over 2 to the L, L greater than 0. Is another way of thinking of that. And now you might say, oh yeah, that's collapsing now. Or you could just plug in convenient values from the original line with A equaling 2 and let N be minus 1. So now we have 1/2. N equal minus 2. Now we have x of minus 2 equaling 1/4, etc. And that's how you could convince yourself of the response that you want to answer for that particular question. And in this case, I would maybe say that you need to get comfortable with saying, okay, this is a to the n. Now, what's the argument inside u if I want to use u as a unit step being a switch, and I want that to be raised to the nth power when n is negative? What needs to be inside the argument for my unit step? Would you do that? You plug in n equal to minus 1, and what happens? You now have u of 1. Is the u at 1 on? Yes, it equals 1. The only thing that we might be missing is if I want it to be strictly negative, then you need to make sure that 0 doesn't turn it on. And 0 would actually turn this one on, wouldn't it? U of minus 0 is the same as u of 0, and u turns on when its argument is 0. That's how you would put the proper argument inside the unit step so that you now have this functional value, a to the n, being turned on only for negative values of n. And so you might see a book write it that way. You might see a book write it as n less than 0. You might see me write it either of those ways. But I want you to be clear what that means or how that notation is being used. Questions on that? Now we can get into the importance of the region of convergence, or let's now examine the z-transform of two different cases where those two different cases are influenced by a pole at 1/2, or R, capital R is equal to 1/2. Here's the first case. So let me say this is now case 1. Let me say here that x of n, oh, I'll call it x sub 1 of n to be case 1. X sub 1 of n is 1/2 to the n for n negative. And just to be thinking about what that looks like or what that represents, I would start plugging in some values just so I get a feel for what x1 of n looks like. What's x sub 1 of minus 1 equal to? 2. What about x sub 1 of minus 2? So that negative index is basically inverting the a is 1/2, we invert it, we get 2, and now we have 2 squared, so this should be 4. Or, one more, and it just keeps going. And we could sketch this and say that at -1, -2, -3, just to get us started, we're at 2, then we're at 4, then we're at 8, and that's now going unbounded as we get further and further into the negative indices. What does the z transform of this sequence look like? Now we just plug in the definition. We know it's from -infinity to infinity, this infinite sum of x sub 1 of n. But this x sub 1 of n is really only valid for negative values of n, so we could actually make that clear by putting this switch into x sub 1 of n, and then we have z to the minus n. And now that we have that switch in there, we can actually say, oh, this is from n equal -infinity up to -1, and now we can get rid of that switch. We can simply put in 1/2 to the n, z to the minus n. Or if we wanted to combine those terms together, we could say, oh, 1/2, another way of writing that is 2 to the minus 1, and that's raised to the n, z to the minus n, or we could say that this is now 2 to the minus n. And that allows us now to collapse that down to looking at something like n equal -infinity to -1, 2z to the minus n. And maybe thinking in terms of negative exponents gets confusing. I sometimes don't like to think about it that way, so let me just do a change of variables. That should be fair game. Let's just make L equal to -n. Obviously, that's going to change our limits, but it shouldn't change the z transform expression. But if I'm changing the limits, I'm going to go ahead and flip-flop. I'm going to go put 1 downstairs and infinity upstairs and index that through L. I now have L equal 1 to infinity, 2z to the L. And maybe I don't even want to think about 2z. You don't need to be thinking about 2z's now either, because I don't want to try to put you to sleep. So I'm going to change that. I'm going to change that to w's. So you won't be thinking about z's. So let's just call this w. But now that we have it written as 2z to the L, what do we know about that particular series and it being well behaved or it converging? What do we know has to be true about w or about 2z? It needs to have a magnitude less than 1. So now we know that 2z's magnitude needs to be less than 1, where the common ratio is 2z, And this is actually a geometric series. Meaning each term now gets modified or changed by this common ratio. It's 2z, then it's 2z squared plus 2z cubed, etc. as we go. And we know that that will be bounded or well behaved when 2z's magnitude is less than 1, but that we can push the 2 to the other side by multiplying both sides by 1/2, and now we have a bound on z, the complex variable. This now says that z is less than 1/2, the magnitude of z is less than 1/2, and that, in fact, establishes our region of convergence. That's where this series converges, is for values of z with z less than 1/2. Yes? So now the question was, what about this lower summation value? Right now it's L equal 1, and before we've always worried about L equal to 0, but so far we haven't said what that equals, have we? We've just said when it will be well behaved. So your question actually is yet to be answered. It doesn't matter whether L is 1, whether L is 10, whether L is 100, we would still need 2z's magnitude to be less than 1. Is that clear? So the index, the lower index, doesn't influence that bound or the region of convergence. It will influence the expression, the final expression for capital X sub 1 of z, where we start that sum. Was the question, did I repeat the question? The question was, okay, we've been looking at problems that have little l equal to 0 usually, and then looking at a region of convergence. But those two issues are actually decoupled. They're not connected to each other. But now let's find what capital X sub 1 of z actually equals. And we can do that using the same strategy that we've learned all semester. And this is why I wanted to write it as W instead of 2z. Not that I can make a very nice W, but at least I can not have to write as much. I don't want to have writer's cramp. I now have omega W plus W squared plus W cubed, etc. That's what the series form for capital X sub 1 of z equals. And our strategy hasn't really changed. We still might want to go to the zoo, right? We might want to play with the tail or keep track of the tail of this series. We want those tails to cancel each other out. And how do we sort of keep the same tail but maybe introduce a new term? What do we have to do to capital X sub 1 of z to have the same tail but yet maybe have the front of that series expansion different? How about if we scale this by W minus 1? Is that okay? And what happens now? Now that first one becomes 1, but the next one becomes just checking to make sure that 2z hasn't sunk in yet. We're still with w's. Sorry. I'm wanting you to make sure that everybody's awake. No one brought their pillow, did they, to class today? Then we have w squared, etc. And the tail now is right there. And that tail will vanish not really vanish, but it's eliminated when we compare those two rows. Here, if I take the second row away from the first row, I have 1 minus the inverse of W. And what do I have on the right? I'm now subtracting the second row from the top row, so I now have a minus 1. So that now I have capital X sub 1 of z is in fact minus 1 over 1 minus W to the minus 1. Or if I wanted that written in terms of W's instead of W inverse, I could scale by 1, which is W over W, and I have minus W over W minus 1. And that's now an expression, a closed form expression, not this series expansion. This is now a closed form expression for the Z transform of that sequence, which was a non-causal sequence, but we really need it in terms of Z since capital X sub 1 is a function of Z, but W was just 2Z. And we could write that differently if we wanted. Maybe we don't like to see it as 2z over 2z minus 1. We can factor out a 2 from the numerator and denominator, and we end up with minus z over z minus 1/2. And when is this z transform, what's its region of convergence? When are we okay with this expression? We needed the absolute value of z less than 1/2. And in this case, then, we can sketch the pole zero diagram in the complex z-plane together with the region of convergence. Where's a 0? Do I have a 0? I have a 0 at the origin. Do I have a pole? At 1/2, so I can draw that here. And where's my region of convergence? What bounds the region of convergence? If I had my compass, how do I adjust that compass's radius? What value do I set that compass at? 1/2, right? So now I have the boundary of my that's supposed to be a circle. And where's my region of convergence? Inside, outside? Maybe I need to see some thumbs here. Where is it? Inside, isn't it? Wait a minute, we've got a 0 in there. Can that be okay? The fact is the poles can't be in our region of convergence, and it's not. It's on the boundary. And where's the unit circle relative to this picture? Here's 1, here's j, here's minus 1, here's minus j. And now if I could draw a circle, this is now the unit circle. What observations can we make for case number 1, which we had a non-causal sequence, and we know its region of convergence, and we know something about that behavior of that non-causal sequence? 1, is that the time response, that's x sub 1 of n, or maybe let me emphasize this and say the time domain response was it bounded or unbounded? All it takes is for us to go back to what we'd sketched. Don't try to remember everything. We can only keep about 7 things in our head at once, right? So why worry about it? Let's just draw some pictures and go back to what we had drawn to remind us. And this is what we had before. What's that time sequence's behavior? Bounded or unbounded? It's unbounded, isn't it? It's going to infinity as time marches towards minus infinity. This is an unbounded time response. So our time domain response is unbounded. And if that actually corresponded to an impulse response of a system, if the system's impulse response, for whatever reason, that's a non-causal system, so it's kind of hard to think about a physical system, but that now is coming in from infinity, it's coming in from unbounded, and then at 0, it's at nothing because we stop at minus 1. But this, we would say, would correspond to an unstable system if that was a system's impulse response. What do we know about the unit circle? So there's one observation. The time domain response is unbounded. The unit circle does not or doesn't lie on top of the region of convergence. Is the region of convergence, is the unit circle shaded? Is the unit circle shaded? Is it a part of that green? That's what I'm trying to say. There's no overlap, is there? The unit circle is not a part of the region of convergence. And that's sort of the connection that you can make right here. When that's true, you know that your response is unbounded. When the unit circle is not in your region of convergence, you have a time domain response that's unbounded. So here's your connection that you can make between the region of convergence and the unit circle and the time domain. One more observation, and that is that the region of convergence is interior to all poles. And that tells us then, based on, I think that was question number 3 in our quiz, then little x of n, in this case, wasn't it x sub 1 of n, we were in case 1, is an anti-causal time sequence. There's no necessarily first or last order to these observations. You could make them at any time. 1, 2, or 3, they could be shuffled. But that information comes from this particular example. So in this case, x sub 1 of n was not equal to 0 for negative values of n, and x sub 1 of n is equal to 0 for non-negative values of n. That's case 1. Case 1 had this for its z transform, z over z minus 1/2, or it's negative, it's minus z over z minus 1/2. But I'm sort of emphasizing the z over z minus 1/2 because maybe that's going to appear shortly. But this is case 1. And this is its region of convergence. Let's look at case 2. Suppose now for case 2 that we have x sub 2 of n is equal to 1/2 to the n, but now we have n greater than or equal to 0. And how could we write that with a switch, using the unit step as a switch? If I didn't want to say comma, n greater than or equal to 0, I just wanted to start typing, what would I hit that with? U of n, the unit step. So there's an equivalent way to write that same time domain sequence. What does this look like as a function of time? What's its value at n equals 0? It's 1. Then it just gets cut by the common ratio, 1/2. So now we're down to 1/2. Then we're down to 1/4, etc. So this is an exponentially decaying sequence. It's well behaved, it's bounded. Let's find its z-transform and its corresponding region of convergence. Capital X sub 2 of z is now this, from the definition, this two-sided infinite sum, x sub 2 of n, but now it's nice to sort of turn that off or on at the appropriate time, z to the minus n. Or this is now the sum from n equal, where are we starting this one? Now it's starting at 0, isn't it? N equals 0 to infinity, 1/2 to the n, z to the minus n. Or I could say that this is now 1/2z to the n. And when is this going to converge? What's the common ratio? One over 2z, right? That's the common ratio. And so now we need the magnitude of 1/2z to be less than 1. Or we can put z on one side of that by multiplying both sides through by the absolute value of z, and we now have 1/2, which could be in a absolute sign or not. We could just have 1/2 being positive. Now we have z outside of 1/2. That's our region of convergence for this particular expression. And now if I called the one w, I might as well call this one something. I don't want to leave it out. Let's call this common ratio w sub 2. Or what is x sub 1 of z? Oh no, this is x sub 2 of z in terms of w. If we did all of that expansion, wouldn't it be 1/1 minus w2? Now we would multiply that second equation by w2 and subtract it, and then we would divide by that 1 minus w2, and we would have 1 coming down from the first or top equation. So if that isn't making sense, go home and do that tonight before dinner, reservation, and work that out. So now we have 1/1 minus w2, which in terms of z Or you might have seen this written as 1 over 1 minus 1/2 z to the minus 1. You can see it written many different ways. If we scale that by z over z, we now have this as z over z minus 1/2. And this is true as long as the absolute value of z is bigger than 1/2. This particular structure for capital X sub 2 of z. Let's now sketch that pole zero diagram and the region of convergence. Do I have any finite zeros? The zeros really don't matter, but I just want you getting comfortable because that last one was inside the region of convergence, wasn't it? In case 1, the zeros just essentially tell us how the system is interconnected with the outside world. The poles tell us how it's shaking, how it's moving. We have a 0 at the origin. Where's our pole? It's at 1/2. Where's our region of convergence? Our region of convergence is now beyond that voided disk in the z-plane. Now we've cut out this little disk, and that's not a part of our region of convergence, but all of the poles are inside that void. We only have one pole, and it's not in the region of convergence. Where's our unit circle? That's supposed to be a unit circle. And now let's make similar observations like we made before. In this case, we know that x sub 2 of n was 1/2 to the n u of n. Or it was 1/2 to the n for n greater than or equal to 0. And I hope that one is pretty clear that the time domain sequence x sub 2 of n is bounded or unbounded. That one's bounded. Or if it corresponded to a system's impulse response, it would be a stable impulse response. What can we say about the region of convergence and the unit circle? Is the unit circle shaded? Is it lying on top of the region of convergence? Both of those, right? So this second observation is that the unit circle lies on top of the region of convergence. Or the unit circle is shaded, and that's our connection. This one now, since the unit circle is inside the region of convergence, or shaded, or on top of the region of convergence, this gives rise to a bounded time domain sequence. The previous one, where was the unit circle relative to the region of convergence? It was not on top of it, was it? It did not belong to the region of convergence, the unit circle. So in this case, our connection says, oh, the unit circle is lying on top of the region of convergence. Boom, our sequence, our time domain sequence is bounded. And finally, as I said, these don't have any particular order to them, but now we know that the region of convergence is, and here's where I don't want to confuse you, but I'm trying to make a point. The region of convergence is unbounded. It was going off to infinity, was it not? It went to infinity. The region of convergence is unbounded and is exterior to all poles. What's the unbounded region of convergence telling us about the time domain sequence? Is it telling us about its bounded behavior? No, it's telling us what? Where it's defined, right? Whether it's whether it's causal, whether it's anti-causal, whether it's two-sided. That's what the region of convergence going to infinity tells us, or being exterior to all the poles. So the region of convergence being outside all of our poles tells us that x sub 2 of n is a causal sequence, or x sub 2 of n is not equal to 0 for n greater than or equal to 0. And x sub 2 of n is equal to 0 when n is negative. What did capital X sub 2 of z look like? Wasn't it z over z minus 1/2? And what was its region of convergence? So if we didn't have that region of convergence on the side, if you just were given z over z minus 1/2, and then somebody gave you this one, which is, I'm covering it up on my tablet, you can't see that region of convergence. So now cover up the region of convergence here, and you still have z over z minus 1/2. Well, its sign has changed, but that wouldn't really make that much difference. What makes the difference in terms of what the corresponding time domain sequence is? For this first one, we had an anti-causal that was unbounded, time sequence. But its z-transform looks just the same structurally as x sub 2 of z's z-transform, z over z minus 1/2. What distinguishes those is the region of convergence. That's why the region of convergence is so important. We have to know what the region of convergence is in order to go back into the time domain uniquely. Do you see, if I just gave you z over z minus 1/2 and said, give me the time domain sequence, somebody might give me the anti-causal form, somebody else might give me the causal form. And can I tell them that either one is wrong? No, because I didn't give them enough information. So in order to go backwards, which is what we want to do with the inverse E transform, we have to know the region of convergence information in addition to the transform itself. So not only do I have to give you the capital X of Z, I also have to tell you the region of convergence so that you know where you're living in terms of the time domain sequence's support region. Is it supported on positive indices? Is it supported on negative indices? Or is it supported on both sides, positive and negative? What I hope this two-case exercise has demonstrated is that what capital X of Z equaling Z over Z minus 1/2 corresponds to in the time domain depends on the region of convergence. I hope I've driven that fact home. Now you have to look at the region of convergence, and then how do you translate that into where it's going to be supported? Well, you can look at your series expansion for capital X of Z and see which limiting case eliminates the negative indices or the positive indices. You don't have to memorize everything. You just have to sort of draw it out. And the other fact that you need to remember is how are the region of convergence areas or patterns related to the poles? The region of convergence blank contains any poles. What goes in the blank? Always, sometimes, never, it depends. What word are we looking for? We never, 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 never have poles in our region of convergence. The region of convergence never contains any poles. That's a fact. And we can take that to the bank, can't we? Because we know how to do our bank account now that we have discrete difference equations. Yes? And we want that to be what? We want that to be going unbounded. That's where we want an unbounded sequence, time domain sequence, right? Okay. That's now the importance of the region of convergence. Let's look at each of those two cases just had one pole. So our regions weren't that involved, were they? We had one that was going unbounded with a central void and another one that was a disk that was contained inside the pole. What happens if we have two poles? What are some possibilities? So let's look at some possibilities with two poles and what that might correspond to in terms of whether the response is bounded or unbounded, etc. Let's look at possibility number one. Suppose now we have the following. Suppose we have a pole at 1/2 and a pole at 3/4. And for this possibility, let's go ahead and say that the region of convergence is outside both poles. This is our z-plane picture. And the green shading is our region of convergence. So in this possibility, our rock is outside all the poles. Just for grins, what's the dominant pole? Or do we have any dominant poles? And what do I mean by dominant pole? It dominates the response. That's the dominant, and so that means that it's the slowest pole. And which of these poles is going to give us the slowest dynamic behavior? And now if you had a two-sided coin, you could flip it if you don't have an answer, but I hope you have an answer. Which pole is dominating? And now you could just plug in some numbers, could you not? You hopefully know, well, what do we know? Well, I'm getting ahead of myself. What's the dominant pole? It's the one closest to, or it's the one closest to the unit circle. 1 in magnitude. If we had a pole at 2, would it make sense to be talking about a dominant pole? Not really, because 1 would be going unbounded and it'd be blowing up our system, wouldn't it? We would smell it burning in no time. So we could rely on our other senses to determine the behavior of that system if we had a pole at 2. And it wouldn't smell very good, would it? So this one, the dominant pole is actually at 3/4. What's the structure of the time domain waveform associated with this picture? And this was an exam 1 problem, wasn't it? What's the structure of the time domain sequence associated with this pole 0 diagram? I hope we haven't forgotten everything we had up in the noodle before exam number 1 or during exam number 1. What's the structure? So we have a pole at 1/2. That's going to be a mode. That tells us it shakes at 1/2. It's not really shaking, is it? It's just collapsing. And we have another one at 3/4. What we don't know is how they are combined, but we could just say, oh, let's make that one alpha 1 and this one alpha 2, and we're good to go. That would be the structure, all depending on where the poles are. So if I said that this is x sub a of n and this is x sub b of n, how would I determine what values of n this is structurally, or this is happening? This structure is happening for what values of little n? Negative, positive, both. Can you tell from this region of convergence? Can you uncover the rock? Can you look at the rock, the region of convergence, and determine what little n is? And if you can't, just go back to our cheat sheet. What's our cheat sheet? Well, little x sub b of n was our dominant one. What if we look at the z transform for capital X sub b of z? Its expression. Do you see how you could answer this question if somebody gave it to you in a job interview? You could just kind of stall for time by showing them, impress them with your knowledge of the Z-transform definition, and you could use that to think through your answer. Right? You go, oh, let's see, region of convergence. Oh, that's supposed to tell me something. You're not saying this, you're thinking this. I need to be able to tell that by the region of convergence. Let me just explain the Z-transform definition and then tell them how that's connected to the region of convergence. And they'll be going, yeah, I like this candidate. Right? So now what do we know now that I've drawn this or sketched this series? So what? What's it telling us? Now you don't want to go cold in your interview. Now what do we do? How do we use this to help us? Now we go back to this region of convergence that maybe they've drawn on a piece of paper or you've drawn on the napkin, and you say, okay, that series is supposed to be well behaved for all values of z that live in this shaded region. And let's pick a convenient value of z. What would be convenient in this shaded region? You could say, oh, let me look at that point, but you know what? I'm going to let that guy go off to infinity. In my thought experiment. So now that point's going off to infinity. That's in the green shaded region. What happens when I let z go to infinity in some of these first few terms? Then capital X sub b of z is going to go unbounded. That's not going to happen. So I need to force this to 0. I need to force this to 0. All of these need to be 0. I now know the little n's where they are supporting that time domain sequence. I know X sub b of n is true for little n non-negative, 0, 1, 2, etc. This now says that X sub b of n is causal and what do I know about, well, how did I find that? Well, I said that the region of convergence was actually unbounded. Don't confuse that with the time domain or the time domain sequence's bounded behavior. What do we know is going to happen to that now that we know that n is greater than or equal to 0? This is now well behaved. It's collapsing. It's exponentially decaying with time. So now we know that x of little n is bounded since we knew the structure. X of n was equal to alpha 1 1/2 to the n plus alpha 2 3/4 to the n for n greater than or equal to 0. Where's the unit circle in this picture? It's at 1, so now you know that it's here, and it's inside, it's on top of the region of convergence. Boom, that tells us what this just said. Our sequence is bounded. Possibility number 2. Let's just go the other extreme. We had a pole at 1/2 and a pole at 3/4. Let's look at what happens here. Do we know the structure of little x of n? And when is it defined for what values of n? And if we don't know, we can continue to go back to this definition. What can we tell about that series relative to the region of convergence? Or combining those two, what can we learn? This again is our thumbs up, thumbs down quiz, is it not? We know in this particular region of convergence an extreme value is when z is equal to 0. So here, z equal to 0 belongs to our region of convergence. And if I plugged in that to any of these, what's going to happen? Well, it'd be disastrous in terms of capital X sub 2 of z unless all of these sequence values are 0. So now we know that little x sub 2 of n is anti-causal. And we know the structure of x sub 2 of n. Is x sub 2 of n bounded or unbounded? And this is now true for n less than 0. Now we're raising a number that's less than 1 to a negative power. What's that going to do? It's going to go unbounded, isn't it? So this now says that x sub 2 of n is unbounded. Where's our unit circle here? Is it in the shaded region? Is it in our region of convergence? No. So that's consistent then with our determining that x sub 2 of n is unbounded. Possibility number 3. We've gone outside, we've gone inside, let's go between. So now we have 1/2, and we have 3/4. And now our region of convergence is a donut or annular. What do we know now about x of n? Now they're not both on one side. One's on one side, one's on the other. If we look at 1/2, where's the region of convergence relative to that 1/2? It's beyond. And what did we know about one poles that were inside or interior to the region of convergence? N is positive or negative? If you just forgot about the 3/4 and let that region of convergence go outside, you know that this is n greater than or equal to 0. What do you know about the 3/4? Now we have a two-sided sequence, right? This pole is interior to the region of convergence. This one, pole is exterior to the region of convergence. And where's the unit circle? It's definitely not shaded, is it? It's outside all of those. So is this waveform bounded or unbounded? If I have 1/2 to the n and n is positive, how's that behaving? 1/2, 1/4, 1/8, that's okay. But what about 3/4? 3/4 to the -1, 3/4 to the minus. That one's going unbounded. So we have a two-sided sequence. The one on the right side is well behaved. The one on the left side is going unbounded. Make sure that starts to make sense, but you could have told that the result has to be unbounded because the unit circle is not shaded. It's not in the rock. And we'll pick up somewhere close to that the next time we meet.